Can you count a list that never ends? You can, and in this chapter you will see how. We start with the simplest idea in mathematics, the set, and build all the way up to infinity. Welcome to Chapter 2, Basic Structures. This chapter builds the pieces that the rest of discrete mathematics stands on. There are 5 of them. A set is a collection of objects. A function gives each input one output. A sequence is an ordered list. A sum adds up many terms, and a matrix is a grid of numbers. We start with the first and most important one, the set. This slide maps the whole chapter so you know where we are going. The left column holds the first 2 parts: sets, the language of sets, set operations, and set identities. Then functions, their types, and the operations we perform on them. The right column holds the rest: sequences and summations with formulas for sums. Then set cardinality, which is the size of a set, including countable sets. And last, matrices and matrix arithmetic. We begin with the very first topic, sets. Section 2.1, Sets. We learn what a set is, how to describe one, the special sets that appear again and again, and how one set can sit inside another. Let us look at the plan for this section. First, the definition of a set. Second, 2 ways to describe a set. The roster method lists the members. Set builder notation states a property the members must satisfy. Third, some important sets that appear everywhere in mathematics, such as the integers and the real numbers. Fourth, 2 special sets, the empty set and the universal set. Fifth, subsets and set equality. Sixth, the cardinality of a set. That simply means its size. Seventh, tuples, which let us talk about ordered collections. And last, the Cartesian product. Use this list as a checklist for the section. Let us start with why sets matter. Sets are one of the basic building blocks for the objects we study in discrete mathematics. They are important for counting, which is a big topic later in the book. And most programming languages give you set operations directly, so this is practical, not only theory. Set theory is a big branch of mathematics on its own. Mathematicians build it from formal starting rules called axioms, and several different systems of them exist. In this course, we do not worry about a formal list of axioms. We use naive set theory, which relies on our natural idea of a collection of objects. Now the definition. A set is an unordered collection of objects. Unordered means the order does not matter. For example, the students in this class form a set, and the chairs in this room form another set. The objects inside a set are called its elements. They are also called its members. Both words mean the same thing, and we say a set contains its elements. There is a special notation for membership. We write a, then a rounded symbol like a curvy E, then capital A. Read that as, A is an element of the set A, or more simply, A is in A. If O is not a member of A, we draw a slash through the same symbol. Read it as, O is not in A. There are 2 ways to describe a set. The first is the roster method. We simply list the members inside curly braces. For example, S equals the set with members of B, C, and D. 2 facts follow from a set being unordered. First, order does not matter. So the set of B, C, D is exactly the same set as B, C, a D. Second, repetition does not matter. Each object is either a member or not, so listing it twice changes nothing. When the pattern is clear, we can use 3 dots instead of writing every member, so all the lowercase letters can be written as a B, C, D, Z. Let us work through 4 examples of the roster method. First, the vowels of the English alphabet. V equals the set E, I, O, U. Second, the odd positive integers below 10. O equals 1, 3, 5, 7, 9. Third, the positive integers below 100. That is too long to write out, so we list the start and use 3 dots. S equals 1, 2, 3, 99. Fourth, the integers below 0. This one has no smallest member, so the 3 dots go on the left. S equals ... minus 3, minus 2, minus 1. The 3 dots always mean the same thing. Continue the obvious pattern. Some sets are so common that they get their own letters, written in a blackboard bold style. Learn these well because we use them constantly. Capital N is the set of natural numbers, 0, 1, 2, 3, and so on. Capital Z is the set of integers. These are the whole numbers going both ways, positive and negative, with 0 in the middle. Capital Z with a small plus sign is the set of positive integers, 1, 2, 3, and so on. Capital R is the set of all real numbers. That is every point on the number line. Capital R with a plus is the set of positive real numbers. Capital C is the set of complex numbers. And capital Q is the set of rational numbers, that is, the fractions. One caution about the first row. Some books leave 0 out of the natural numbers, so always check the convention a book is using. The second way to describe a set is set builder notation. Instead of listing the members, we state the property that every member must satisfy. We write a curly brace, then a variable such as x, then a vertical bar read as such that, then the property, then a closing brace. For example, S is the set of all x such that x is a positive integer below 100. The same set O can be written 2 ways. All x such that x is an odd positive integer below 10. Or more compactly, all x drawn from the positive integers such that x is odd and x is below 10. We can also use a predicate, which is a property named with a letter. S equals all x such that P of x holds. For example, all x such that prime of x, meaning all the prime numbers. One last example. The positive rational numbers are all x and r such that x equals P over Q for some positive integers P and Q. Intervals of real numbers are just sets, and we describe them with set builder notation. A square bracket means the endpoint is included. A round bracket means it is not. First, 2 square brackets from a to b that is all x with a less than or equal to x, and x less than or equal to b both ends are in. Second square bracket, a round bracket b here the left end is in, and the right end is out. Third round bracket, a square bracket b that is the other way round. The left end is out and the right end is in. Fourth, 2 round brackets from a to b neither end is in. We give 2 of these names. When both endpoints are included, we call it a closed interval. When neither endpoint is included, we call it an open interval. 2 special sets deserve their own names. The first is the universal set. Written with a capital U, it holds everything that is currently under consideration in our problem. Sometimes we leave it unwritten and just understand it. Sometimes we state it, and its contents depend on the problem. For one question, you might be all integers. For another, it might be all students in a school. The second special set is the empty set. It has no elements at all. We write it as a circle with a slash through it, or as an empty pair of curly braces. The picture is a Venn diagram. The rectangle is the universal set U, the oval inside it is the set V of vowels, E, I, O, and U. Venn diagrams like this one are named after John Venn. They help us picture how sets sit inside one another. This slide shows a famous puzzle called Russell's paradox. Let capital S be the set of all sets that are not members of themselves. Now we ask a simple question. Is S a member of itself? Watch what happens. Suppose S is a member of itself. Then, by the rule that defines S, it must not be a member of itself. That is a contradiction. Now suppose the opposite. S is not a member of itself. Then it fits the rule perfectly, so it should be a member of itself. Again, a contradiction. Either answer breaks itself. The mathematician in the photo, Bertrand Russell, found this paradox. The next slide gives a friendlier version of it. Let us try a friendly version of the same paradox. Henry is a barber. He shaves all the people who do not shave themselves and nobody else. The question is simple. Does Henry shave himself? Try the first answer. Suppose Henry does shave himself. Then he shaves someone who shaves themselves and his own rule forbids that. Contradiction. Try the other answer. Suppose Henry does not shave himself. Then he is exactly the kind of person his rule says he must shave. Contradiction again. Both answers break, and that is the whole point. Some descriptions that sound reasonable do not describe anything at all. This is why naive set theory needs careful rules about which collections may be called sets. 2 reminders before we go on. First, sets can be members of other sets. Look at the first example. It is one set with 3 members. The set containing 1, 2, and 3, then the single object A, and then the set containing B and C. A member of a set can itself be a whole set. The second example is a set whose 4 members are N, Z, Q, and R. Each one is a famous set of numbers. Now the second reminder, and please be careful here. The empty set is not the same thing as a set that contains the empty set. The empty set has 0 elements, but the set with curly braces around the empty set has exactly 1 element, and that element is the empty set. One is empty, the other is not. Now we say precisely when 2 sets are equal. 2 sets are equal if, and only if they have exactly the same elements. In symbols, A equals B if and only if for all x. X is in A exactly when x is in B. The two-headed arrow means exactly when. Now the practical consequence. A set is unordered and it never counts repeats. So the order you list the elements in does not matter. The set 1, 3, 5 equals the set 3, 5, 1. And listing an element more than once changes nothing. Only which elements are present matters. Now the idea of a subset. We say A is a subset of B if every element of A is also an element of B. In symbols, for all x, if x is in A then x is in B, so B holds everything that A holds and maybe more. 2 special facts hold for every set as first. The empty set is a subset of Sy. To be a subset we need. If A is in the empty set, then A is in S, but the start of that sentence is always false, and an if-then statement with a false start is always true. So the empty set is a subset of everything. Second, every set is a subset of itself. That is because if A is in S, then A is in S, which is obviously always true. How do we actually prove one set is a subset of another, or show that it is not? To prove A is a subset of B, we show that whenever X belongs to A, X also belongs to B. We take a general element of A and argue it must be in B. To show A is not a subset of B, we only need one counterexample. A single element that is in A but not in B settles it. Let us look at two examples. The computer science majors at your school form a subset of all the students at your school, because every such major is indeed a student. Second, the integers whose squares are below 100 are not a subset of the non-negative integers. Take -5. Its square is 25, which is below 100, so it is in the first set. But -5 is negative, so it is not in the second. One counterexample is enough. Let us look at set equality again, this time from a logic point of view. We already know that A equals B means. For all x, x is in A exactly when x is in B. Now read that inner part. It is a biconditional, and exactly when. And a biconditional is really two if-then statements joined by and. So we rewrite it. For all x, if x is in A, then x is in B, and also if x is in B, then x is in A, two arrows, one each way. The next slide reads those two halves back as statements about sets. Now read the two halves back as statements about sets. The first half says, for all x, if x is in A, then x is in B. In plain words, everything in A is also in B. That is exactly the definition of A is a subset of B. The second half says, for all x, if x is in B, then x is in A. Everything in B is also in A. That is, B is a subset of A. Put them together. A equals B exactly when A is a subset of B, and B is a subset of A. And that gives us a proof technique we will use again and again. To show two sets are equal, show each one is a subset of the other. A proper subset is a subset that is not the whole thing. If A is a subset of B, but A is not equal to B, we call it a proper subset of B. We write it with the pointed less than symbol, without the line under it, pointing at B. Two things are true when it is a proper subset of B for all x. If x is in A, then x is in B, and there exists some x that is in B, but not in A. Read that in words. The first part says everything in A is also in B, so A is a subset. The second part says B has at least one extra element, so the two sets are not equal. The Venn diagram shows it. The big rectangle is the universal set U, the larger circle is B, and the smaller circle A sits fully inside B, with room to spare. That extra room is the element B has but A does not. Cardinality just means the size of a set, how many elements it has. If a set S has exactly n distinct elements, where n is a whole number that is 0 or more, we say S is finite. If it has no such finite count, we say S is infinite. For a finite set A, its cardinality is written as a between two vertical bars. It is the number of distinct elements of A. Watch the word distinct. Repeats do not count twice. We work through examples on the next slide. Now let us count some sets, one line at a time. Line 1, the empty set. It has no elements at all, so its cardinality is 0. Line 2, the letters of the English alphabet, A through Z, that is 26 elements. Line 3, the set 1, 2, 3, 3 distinct elements, so the answer is 3. Line 4. Look carefully at this one. The set whose only element is the empty set is not empty. It holds exactly one thing, and that thing happens to be the empty set. So its cardinality is 1, not 0. Line 5. The set of all integers. The counting never ends, so this set is infinite, and cardinality as a number does not apply. The power set collects together every possible subset of a set. The set of all subsets of a set A is called the power set of A. We write it with a fancy script letter P, then in brackets. Let us build one. Let it be the set containing and B. What are all of its subsets? First, the empty set, which is a subset of everything. Then the set with just A, then the set with just B. And finally the whole set, A and B together. So the power set of A has 4 members, and each member is itself a set. Now a lovely rule. If a set has n elements, its power set has 2 to the power n elements. Our set A had 2 elements, so its power set has 2 to the power 2, which is 4. That matches exactly. We prove this counting rule in chapters 5 and 6. So far our collections have been unordered, but sometimes order matters, and for that we use tuples. An ordered in tuple is written as a list inside round brackets. A 1, a 2, up to an n, its first element is a 1, its second is a 2, and so on to the last element. 2 n tuples are equal only when their matching positions agree. The first equals the first, the second equals the second, and so on. A tuple with 2 entries is called an ordered pair. So the pair A B equals the pair C, D exactly when A equals C and B equals D. Now the key difference from sets. A tuple is ordered and it may repeat entries. The pair 1, 2 is not the same as the pair 2, 1 even though the set 1, 2 is the same as the set 2, 1. The Cartesian product builds ordered pairs out of 2 sets. The Cartesian product of A and B, written across B with a multiplication cross, is the set of all ordered pairs A comma B, where A comes from A and B comes from B. The order matters inside each pair. The first slot always comes from A, and the second slot always comes from B. The idea is named after René Descartes in the picture. On the next slide, we build one Cartesian product in full. Let us build one Cartesian product in full. Let it be the set A, let B be the set 1, 2, 3. We must pair every element of A with every element of B. Row 1. Hold the first slot at A and let the second slot run through B. That gives the pairs a 1, a 2, and a 3. Row 2. Now hold the first slot at B and run the second slot again. That gives B1, B2, and B3. Count what we have. A has 2 elements and B has 3, so the table has 2 rows and 3 columns, which is 6 cells. 6 ordered pairs, 1 per cell, and none is missing. One more definition before we move on. A subset R of a cross B is called a relation from A to B. Read that slowly. The Cartesian product holds every possible pair. A relation simply keeps some of those pairs and drops the rest. The pairs you keep are the ones you call related. Let us try it on the 6 pairs we just built. Keep the pair A1 and the pair B3. Drop the other 4. What is left is a relation R with just those 2 pairs. That is all a relation is at this stage. We study them properly in Chapter 9. The Cartesian product works for more than 2 sets too. The Cartesian product of the sets A1, A2, up to an n is the set of ordered in tuples, where each entry comes from the matching set. so the first slot comes from the first set, the second slot from the second set, and so on. Now an example with 3 sets. Let it be 0 and 1. Let B be 1 and 2. Let C be 0, 1 and 2. We must find a cross B cross C. We work it out on the next 2 slides. Let us set the problem up before we write anything down. Step 1. Name the sets in order. A is 0 and 1. B is 1 and 2. C is 0, 1 and 2. Step 2. Say what one answer looks like. Each element is a triple, a first entry from A, a second from B, a third from C. Step 3. Count them before you list them. 2 choices for the first slot, 2 for the second, 3 for the third. 2 times 2 times 3 is 12, so we expect 12 triples. Step 4. Now we list them in a fixed order. Hold the first entry, hold the second entry, and let the third entry run. That keeps us from missing one. We do that on the next slide. Now all 12 triples, one row at a time. Row 1. The first entry is 0 and the second entry is 1. Let the third entry run through 0, 1, and 2. That gives 0, 1, 0, 0, 1, 1, and 0, 1, 2. Row 2. The first entry is still 0 and the second entry is now 2. That gives 0, 2, 0, 0, 2, 1, and 0, 2, 2. Row 3. The first entry is 1 and the second entry is 1. That gives 1, 1, 0, 1, 1, 1, and 1, 1, 2. Row 4. The first entry is 1 and the second entry is 2. That gives 1, 2, 0, 1, 2, 1, and 1, 2, 2. Count what we have. 4 rows of 3 is 12. That matches the count we predicted, so nothing was missed and nothing was written twice. Now we connect predicates back to sets. Given a predicate P and a domain D, the truth set of P is the set of all elements in the domain that make P true. We write it as the set of X in D such that P of X holds. Read it as the set of all X in D for which P of X is true. Now an example. The domain is the integers, and the predicate says the absolute value of X equals 1. Which integers have absolute value 1? Only -1 and +1. So the truth set is the set containing -1 and 1. This idea lets us turn any statement about for all, or there exists, into a question about a set. Section 2.2. Set operations. So far we have described single sets. Now we learn how to combine them and compare them, just as we add or multiply numbers. Let us look at the plan for this section. First, 4 set operations. Union joins 2 sets. Intersection keeps the part they share. Complementation takes everything outside a set, and difference takes what is in one set but not the other. Then we look again at cardinality, the size of a set, and count the size of a union. After that we list the set identities, which are rules that are always true. Then we learn how to prove such an identity by logic. And finally we learn a second way to prove one, using membership tables. Use this list as a checklist. A short but important idea. 2 things you have already studied, propositional calculus and set theory, are secretly the same kind of system. We call it a Boolean algebra, and we study it fully in Chapter 12. What this means for us now is that every set operation has a twin in logic. Union behaves like or, intersection behaves like and, complement behaves like not, so the rules will feel familiar. And remember one rule that never changes. There is always a universal set, written U, and every set we talk about lives inside U. It is the box that holds everything under discussion. The union of A and B, written a cup B, is the set of all x such that x is in A or x is in B. Read the cup as the word or. An element joins the union if it belongs to A or to B or to both. In the Venn diagram, both circles are shaded. The whole of it together with the whole of B, nothing is left out. We work an example on the next slide. Now a worked example. We start with the set 1, 2, 3, union the set 3, 4, 5. Step 1. Take everything from both lists and do not tidy up yet. That gives 1, 2, 3, 3, 4, 5. The 3 turned up twice because it is in both sets. Step 2. A set never lists the same thing twice, so we write the 3 only once. The answer is 1, 2, 3, 4, 5. 5 elements, not 6. The intersection of A and B, written a cap B, is the set of all x such that x is in A and x is in B. Read the cap as the word and. Only the elements shared by both sets survive. In the Venn diagram, just the overlapping lens in the middle is shaded. One special word. If two sets share nothing, their intersection is the empty set, and we call them disjoint. We work 2 examples on the next slide. Now 2 examples. The method is the same each time. Check each element of the first set against the second. First, the set 1, 2, 3 intersect the set 3, 4, 5. Is 1 in the second set? No. Is 2? No. Is 3? Yes. So only 3 survives, and the answer is the set containing 3. Second, the set 1, 2, 3 intersect the set 4, 5, 6. Check again. 1 is not there, 2 is not there, 3 is not there. Nothing survives, so the answer is the empty set. That second pair share nothing at all, so we call them disjoint. The complement of A, with respect to the universe U, is written A with a bar on top. It is everything in the universe that is not in A. In symbols, the set of X in U such that X is not in A. Another common notation is with a small letter C raised beside it. In the Venn diagram, the whole box is shaded, except the white circle A carved out of it. The shaded part is the complement. Watch this point. The answer always depends on the universe U you have named. Change U and the complement changes with it. We work an example next. Now a worked example. Let U be the positive integers below 100. We want the complement of the set of X with X greater than 70. Step 1. The complement keeps everything else in U, so we want the X in U for which X is not greater than 70. Step 2. Turn that into plain words. Not greater than 70 means less than or equal to 70. So the answer is the set of X with X less than or equal to 70. The difference of A and B, written a minus B, is the set of elements that are in A but not in B. In symbols, the set of X such that X is in A and X is not in B. There is a neat second form. A minus B equals a intersect the complement of B, so in A, but not in B is the same as in A, and in not B for this reason. We also call it the complement of B with respect to A. In the Venn diagram, we shade the part of circle A that does not overlap B, the left crescent of A only. How big is a union? The size of a union B equals the size of A plus the size of B minus the size of intersect B. We call this inclusion and exclusion. Now why we subtract. If we simply add the size of A and the size of B, the elements that live in both sets get counted twice, once inside A and once inside B, so we subtract the size of the overlap once to fix the double count. An example in plain words. Let A be the maths majors and B the computer science majors in your class. To count the students who are maths majors or computer science majors, add the two groups, then subtract the students who are both, because you counted them twice. In the diagram, the shaded overlap is exactly the part we subtract. We extend this to n sets in chapters 6 and 8. Let us practice all four operations on one example. The universe U is the whole numbers 0 through 10. A is 1 through 5. B is 4 through 8. Line 1. A union B means in A or in B sweep both lists and drop the repeats. The answer is 1 through 8. Line 2. A intersect B means in both. Only 4 and 5 appear in both, so the answer is 4 and 5. Line 3. A bar means in U but not in A, cross out 1 through 5. What is left is 0, 6, 7, 8, 9, and 10. Line 4. B bar means in U but not in B, cross out 4 through 8. What is left is 0, 1, 2, 3, 9, and 10. Line 5. A minus B means in A but not in B, start with 1 through 5 and drop 4 and 5. That leaves 1, 2, 3. Line 6. B minus A means in B but not in A, start with 4 through 8 and drop 4 and 5. That leaves 6, 7, 8. Compare the last two answers. They are different. Subtracting sets is not symmetric. Now the set identities, rules that are always true, no matter which sets you pick. Read them like the rules of arithmetic. The identity laws. A union, the empty set, is just A, and an intersect, the universe, is just A. Those add nothing new and take nothing away. The domination laws. A union, the universe, is the whole universe, and an intersect, the empty set, is the empty set. The idempotent laws. A union A is A, and an intersect A is A. Combining a set with itself changes nothing. And the complementation law, sometimes called double complement. The complement of A is A again, because negating twice brings you back. More laws follow on the next slide. Commutative, associative, distributive, De Morgan, absorption, and complement laws. This is the second group of set identities. An identity is a rule that is always true for any sets. Look at the commutative laws first. The symbol with the cup shape which opens upward means union. A union B equals B union A. The order does not matter. The same holds for intersection. The symbol that opens downward like a cap means intersection. A intersect B equals B intersect A. Next, the associative laws. They say the grouping does not matter. A union the bracket B union C equals the bracket a union B. Union C the same holds for intersection. Finally, the distributive laws. They mix the two operations. A intersect the bracket B union C equals the bracket A intersect B, union the bracket A intersect C. And the second one. A union the bracket B intersect C equals the bracket A union B. Intersect the bracket A union C. These behave much like multiply and add in ordinary algebra. This is the last group of set identities. First, the De Morgan laws. These are very important. A bar drawn over a whole expression means complement, that is, everything that is not in it. The first De Morgan law says the complement of a union B equals the complement of A. Intersect the complement of B in words. If something is not in either set, then it is outside A and outside B. The second law says the complement of A intersect B equals the complement of A, union the complement of B. Next, the absorption laws. A union the bracket A intersect B is just A, and a intersect the bracket a union B is just A. The extra part is absorbed and adds nothing. Last, the complement laws. A union its own complement equals U, the universal set, because together they cover everything. And the intersect its own complement is the empty set, because nothing can be inside a set and outside it at the same time. How do we prove that two sets are always equal? There are three common methods. Method 1. Show that each side is a subset of the other. If the left side sits inside the right side and the right side sits inside the left side, they must be the same set. Method 2. Use set builder notation. Describe each side with the rule the set of all x such that some condition holds, then use the logic laws from Chapter 1. Method 3. Build a membership table. It works like a truth table. For every possible combination of in or out, we compute whether an element belongs to the left side and to the right side. We write 1 for in and 0 for out. If the two columns match on every row, the identity holds. The key idea is that each method turns a question about sets into a question about logic, which we already know how to answer. Let us prove the second De Morgan law as a worked example. We want to show that the complement of A intersect B equals the complement of A, union the complement of B. Remember method 1 from the previous slide. Two sets are equal exactly when each one is a subset of the other. So we must prove two things. Part 1. The complement of A intersect B is a subset of the complement of a union the complement of B. Part 2. The other direction. The complement of a union the complement of B is a subset of the complement of A intersect B. If both directions hold, the two sets are equal. We prove part 1 next and part 2 after that. Now the first direction. To show a subset, we take a typical element x on the left and show it must be on the right. Read the table from top to bottom. We assume x is in the complement of A intersect B. By the definition of complement, that means x is not in A intersect B. By the definition of intersection, being in an intersect B means x is in A and x is in B, so not being in it means not in brackets x in A and x in B. Now we apply the first De Morgan law for propositional logic. It turns not A and B into not A or not B. By the definition of negation, we can write that as x is not in A or x is not in B. By the definition of complement, not in a means in the complement of A, and the same for B. And by the definition of union, that is exactly saying x is in the complement of a union the complement of B that finishes direction 1. Now the second direction, going the other way. We assume x is on the right, and we must show it is on the left. We assume x is in the complement of a union, the complement of B. By the definition of union, that means x is in the complement of A, or x is in the complement of B. By the definition of complement, that means x is not in A, or x is not in B. By the definition of negation, we can write this as not x in A, or not x in B. Now we use the first De Morgan law for propositional logic in reverse. It turns not or not B into not, in brackets, A and B. By the definition of intersection, x in A and x in B is the same as x in intersect B, so we now have not x in intersect B. Finally, by the definition of complement, that says x is in the complement of an intersect. B both directions are proved, so the two sets are equal. Now the same law proved a second way with set builder notation. Set builder notation writes a set as all x such that some condition is true. Each line equals the line above it, and the reason sits on the right. We start with the complement of an intersect B. Step 1. By the definition of complement, that is the set of all x that are not in an intersect B. Step 2. The not in symbol is just shorthand. Write it out as not x is in an intersect B. Step 3. By the definition of intersection, x is in an intersect B means x is in A and x is in B. Step 4. Now applied to Morgan in logic. Not A and B becomes not A or not B, so we get not x in A or not x in B. We finish the chain on the next slide. We pick the chain up from the line we reached. All x such that not x in A or not x in B. Step 5. Fold each negation back into the not in symbol, so it reads x is not in A or x is not in B. Step 6. By the definition of complement, not in a means in a bar, and not in B means in B bar. Step 7. By the definition of union, in a bar or in B bar means in a bar union B bar. Step 8. Now just read the notation. The set of all x that lie in a bar union B bar is a bar union B bar itself. That is the right-hand side we wanted. Same result as before, reached by a second method. Now method 3 in action, a membership table. We want to check the distributive law. A union the bracket B intersect C equals the bracket a union B. Intersect the bracket a union C. Let us plan the table first. Step 1. Fix the code. We write 1 when an element is in a set and 0 when it is not. So every cell holds a 0 or a 1. Step 2. Count the rows. There are 3 sets and each one is either in or out. 2 times 2 times 2 is 8, so the table has 8 rows. Step 3. Do not jump to the answer. Add 1 helper column for each small piece. B intersect C, a union B and a union C. Step 4. Then compare the 2 sides. The 5th column is the left side of the law. The 8th column is the right side. If they match on every row, the law holds. We split the 8 rows over the next 2 slides. These are the 4 rows where it is 1, that is, where the element is inside A. Row 1. B and C are both 1, so B intersect C is 1. A union that is 1. On the right, a union B is 1, a union C is 1 and 1 is 1. Both sides give 1. Row 2. C is now 0, so B intersect C is 0. But it is 1, so a union 0 is still 1. On the right, both unions are 1, so the last column is 1. Both sides agree again. Row 3. B is 0 and C is 1. B intersect C is 0 and a union 0 is 1. On the right, both unions contain A, so both are 1 and the answer is 1. Row 4. B and C are both 0. B intersect C is 0 and a union 0 is 1. On the right, both unions are 1 again. See the pattern. Once there is 1, a sits in every union, so both sides are 1. Now the 4 rows where it is 0. Row 5. B and C are both 1, so B intersect C is 1, and 0 union 1 is 1. On the right, a union B is 1 and a union C is 1, so the answer is 1. Both sides give 1. Row 6. B is 1 and C is 0. B intersect C is 0, and 0 union 0 is 0. On the right, a union B is 1, but a union C is 0, and 1 and 0 is 0. Both sides give 0. Row 7. B is 0 and C is 1. B intersect C is 0, so the left side is 0. On the right, a union B is 0, so the last column is 0. Both sides give 0. Row 8, everything is 0, so both sides are 0. Now compare column 5 with column 8 across all 8 rows. They match every time. The two sets are equal, and the distributive law is proved. So far, we have taken the union or intersection of two sets. Now we do it for many sets at once. Suppose we have a whole list of sets, a sub 1, a sub 2, and so on up to a sub n. We call this an index collection, because each set has an index number. The big union symbol, the tall cup with I equals 1 written below and n above, is a short way to write a sub 1, union a sub 2, and so on up to a sub n. It means every element that is in at least one of the sets. The big intersection symbol, the tall cap, means a sub 1, intersect a sub 2, and so on up to a sub n. It means every element that is in all of the sets. These are well defined, meaning there is no confusion about the answer, because union and intersection are associative. The order in which we group the sets does not matter. Let us see an example. For each index I, we define the set as sub I to be all the whole numbers starting at I and going up forever. So a sub 1 is 1, 2, 3, and up. A sub 2 is 2, 3, 4, and up. Each later set is a bit smaller because it starts higher. Now take the big union from I equals 1 to n. The union collects everything in any of the sets. Since a sub 1 already holds 1, 2, 3, and up, the union is just 1, 2, 3, and up. Now take the big intersection from I equals 1 to n. The intersection keeps only what is in every set. A number survives only if it is in all of them, including the one that starts highest, which is a sub n. So the intersection is n, n plus 1, n plus 2, and up, which is exactly a sub n. Section 2.3, Functions. A function is a rule that takes each input and gives back exactly one output. You already use them, giving each student one grade or adding one to a number. Let us look at the plan for this section. First, the definition of a function with 4 key words that name its parts: the domain, the codomain, the image, and the preimage. Second, 3 special kinds of function: injection, which means one-to-one, surjection, which means onto, and bijection, which is both at once. Third, the inverse function, which undoes a function. Fourth, function composition, which means doing one function after another. Fifth, graphing functions, that is, drawing them as a picture. Sixth, 3 important building blocks: the floor function, the ceiling function, and the factorial. Use this list as a map for what is coming. Now the definition of a function. Let A and B be 2 sets, both non-empty, meaning neither one is empty. A function f from A to B, which we write as f colon A arrow B, is a rule. The rule takes each element of A and assigns to it exactly one element of B. The 2 important words are each and exactly one. Every element of A must get an assignment, and it gets only 1, never 2. When the rule sends the element A to the element B, we write f of equals B, and we say B is the image of A. Functions have other names too. Sometimes we call them mappings and sometimes transformations. Let us look at a picture of one. Look at the picture. The left side holds 4 students. The right side holds the grades. Each arrow shows the grade one student received. Carlota Rodriguez maps to grade A. Sandy Patel maps to B. Jalen Williams, also maps to B. Kathy Scott maps to A. Two things are worth watching. First, every student has an arrow. Nobody is left out. Second, no student has two arrows. Each one gets exactly one grade. That is what makes this a function. Watch two more details. Two students can share a grade, and the grades C, D, and F are used by nobody. Both of those are allowed. Now a second way to look at a function. Remember that a relation from A to B is a set of ordered pairs, where the first part comes from A and the second part comes from B. A function is a special relation. It is a subset of a cross B with one restriction. No two pairs may share the same first element. In plain words, a function from A to B holds one and only one ordered pair for every element in A. The two formulas on the slide say this exactly. We read them one at a time on the next slide. Let us read the two rules one at a time. The first formula says, for all x, if x is in A, then there exists a y such that y is in B and the pair x. Y is in F in plain words. Every input has at least one output. Nothing in A is left without an arrow. The second formula says, if the pair x, y1 is in F and the pair x, y2 is in F, then y1 equals y2. In plain words, an input cannot have two different outputs, so every input has at most one output. Now put them together. At least one and at most one means exactly one. That is the whole definition of a function, written in logic. Now we name the parts of a function f from A to B. We say f maps A to B, or that f is a mapping from A to B. The set A is called the domain of f, that is where the inputs come from. The set B is called the codomain of f, that is the target set the outputs are allowed to land in. Now suppose f of A equals B, then B is called the image of A under f, and it is called a preimage of B. The little picture shows it. The arrow labeled F takes the point A on the left to the point B on the right. Last on this slide, the range of F, written F of A, it is the set of all images of all the points in A. That is, every output the function actually produces. The range can be smaller than the codomain. When are two functions equal? Not just when their formulas look alike. Three things must match. 1. The domain. The same rule on the integers and on the real numbers gives two different functions because their inputs differ. 2. The codomain. The same arrows but aimed at a larger target set is also a different function. We saw this with onto. The codomain you name matters. 3. The value at every input. They must send each element of the domain to the same element of the codomain. One disagreement anywhere is enough to make them different. Only when all three match are the two functions equal. A function does not have to be given in only one way. There are several ways to describe the same idea of one output per input. First, an explicit statement of the assignment. You simply list, for each input, which output it goes to. The students and grades example works like this. Second, a formula. For example, f of x equals x plus 1. This tells you how to compute the output from the input. Third, a computer program. For example, a Java program that takes an integer n and returns the nth Fibonacci number. All three describe functions, just in different styles. We will meet the Fibonacci numbers again in the next section, and again in Chapter 5. Let us practice with one particular function f from A to B, shown by the arrow diagram. The arrows tell us, A goes to Z, B goes to Y, C goes to Z, and D goes to Z. What is f of a? The arrow from a points to z, so f of a is z. What is the image of D? The arrow from D points to Z, so the image is Z. What is the domain of F? It is the whole starting set A. What is the codomain? It is the whole target set B. What is the preimage of Y? We ask which element maps to Y, only B does, so the preimage of Y is B. What is f of A, the range? It is the set of all outputs actually used, which is Y and Z watch the element X. It is never hit. Finally, what are the preimages of Z? We ask which elements map to Z, that is a C and D, so the preimages of Z form the set a C, D. Sometimes we apply a function not to a single element but to a whole subset. If S is a subset of A, then the image of S, written f of S, is the set of all outputs f of S, as S runs over the elements of S. Let us use the same function as before. A goes to Z, B goes to Y, C goes to Z, and D goes to Z. First question. What is f of the set of B, C? We collect the images. A gives Z, B gives Y, C gives Z, remove the repeat, and we get the set Y, Z. Second question. What is f of the set C, D? Here C gives Z and D gives Z, so the image is just the set containing Z. A set never lists the same element twice. Now we meet the first special kind of function, the injection, also called one-to-one. A function f is one-to-one if, whenever f of a equals f of b, it must follow that it equals b. A function with this property is called an injection. Let us say it in plain words. One-to-one means different inputs always give different outputs. No two arrows are allowed to land on the same target. Look at the picture. Here A goes to Y, B goes to X, C goes to Z, and D goes to W. All four targets are different, so this is an injection. Watch the element V on the right. No arrow ever uses it, and that is perfectly fine. Being one-to-one only forbids two inputs sharing a target. It does not require every target to be used. The second special kind of function is the surjection, also called onto. A function f from A to B is onto if, for every element B in the codomain B, there is at least one element in the domain A with f of a equal to B. Such a function is called a surjection. In symbols, for all B in B, there exists an A in A, such that f of a equals B. In plain words, every target in B is hit by at least one arrow, and nothing in B is left out. Look at the picture. Here A goes to Y, B goes to X, C goes to Z, and D goes to Z. Every element of B, that is X, Y, and Z, receives an arrow, so this function is onto. But watch, it is not one-to-one because Z is hit twice by both C and D. The third special kind of function combines the two we just learned. A function is a one-to-one correspondence, or a bijection, if it is both one-to-one and onto. Think of a bijection as a perfect pairing between the two sets. Every target is used because the function is onto, and every target is used exactly once because the function is one-to-one. Look at the picture. Here A goes to Z, B goes to Y, C goes to X, and D goes to W. Every element of B receives exactly one arrow, and nothing is left out or doubled. So this function is a bijection. As we will see next, bijections are special because they can be reversed. This slide is a recipe card. Suppose f is a function from A to B, and we want to decide whether it is one-to-one or onto. Let us read the four cases. To show f is injective, take two arbitrary elements x and y of A, Assume f of x equals f of y, and then argue that x must equal y. To show f is not injective, it is enough to find two particular different elements with the same output. So x is not equal to y, but f of x equals f of y. To show f is surjective, take an arbitrary target y and b, and find some input x in whose output is y. To show f is not surjective, find one particular target y and b that no input reaches. The general lesson is in the warning box. To prove a property, you must reason about an arbitrary element, but to disprove it, one counterexample is enough. Let us work the first example. The function f goes from the set of b, c, d to the set 1, 2, 3. F of O is 3, f of b is 2, f of c is 1, and f of d is 3. Is f onto? Step 1. Write down the codomain because onto is a claim about the codomain. It is the set 1, 2, 3. Step 2. Take the first target 1. Is there an input that reaches it? Yes, f of c is 1, tick. Step 3. Take the second target 2. F of b is 2, tick. Step 4. Take the third target 3. F of O is 3, tick. And d also maps to 3, which is allowed. Step 5. Every target was reached, so f is onto. Now the warning. Suppose we keep the same arrows but call the codomain 1, 2, 3, 4. Nothing maps to 4, so the same function is no longer onto. Onto always depends on the codomain you name. Now the second example. Is f of x equals x squared from the integers to the integers onto? Step 1. Name the two sets. The domain is the integers, and the codomain is also the integers. Step 2. Remember the rule. To disprove onto, we do not need a general argument. One target that nothing reaches is enough. Step 3. Where should we look? A square is never negative, so a negative target is a good guess. Let us try -1. Step 4. Is there an integer x with x squared equal to -1? No. Squaring any integer gives 0 or a positive number. Step 5. So -1 sits in the codomain but has no preimage. That single missed target settles it. The function is not onto. Now we come to inverse functions. Let f be a bijection from a to b, then the inverse of f, written f with a small -1 above it, is the function that goes the other way, from b back to a. It is defined like this: f inverse of y equals x, exactly when f of x equals y. In plain words, the inverse simply runs the arrows backwards. It takes each output and sends it back to the one input that produced it. Look at the picture. The blue arrow f carries a forward to b, and the amber arrow f inverse carries b back to a. And now the warning to carry with you. No inverse exists unless f is a bijection. The next slide shows exactly what goes wrong otherwise. Why does the inverse need a bijection? Think about what f inverse must do. To be a function, it has to give exactly one answer for every y and b. First case. Suppose f is not onto, then some y and b has no preimage at all. Nothing maps to it. So f inverse of y has nothing to return and the rule breaks down. Second case. Suppose f is not 1-to-1, then some y has several preimages. 2 or more inputs both landed on it. So f inverse of y cannot choose between them, and again the rule breaks down. Only a bijection avoids both traps. It gives exactly one input for each output, so only a bijection can be reversed. This slide shows the inverse in action with a concrete bijection. The left picture is the function f from a to b. Its arrows are a goes to x, b goes to v, c goes to y, and d goes to w. Because f is a bijection, every element of b is hit exactly once, so we can safely reverse it. The right picture is the inverse function, which goes from b back to a. To build it, we simply flip every arrow. So v, which came from b, now goes back to bw, which came from d, goes back to dx, which came from a, goes back to a, and y, which came from c, goes back to c. The amber color marks that we are traveling backwards. The picture to remember is this. The inverse of a bijection is the same set of arrows, drawn in the opposite direction. Let us finish inverse functions with 3 questions. Work each one the same way. First test whether the function is a bijection. Only then try to build the inverse. Example 1. F goes from the set of B, C to the set 1, 2, 3 with f of equal to 2, f of B equal to 3, and f of C equal to 1. Test the bijection. 1 is hit once, 2 is hit once, 3 is hit once. So yes. Now turn each arrow round. F inverse of 1 is C, F inverse of 2 is A, and F inverse of 3 is B. Example 2. F goes from the integers to the integers, and f of x equals x plus 1. Every integer target is reached by exactly one input, so it is a bijection. The function adds 1, so the inverse subtracts 1. F inverse of y equals y minus 1. The third question is on the next slide, and it goes differently. Now the third question. F goes from the real numbers to the real numbers, and f of x equals x squared. Is it invertible? Step 1. Test 1 to 1 before you do anything else. That means looking for 2 different inputs that share an output. Step 2. Squaring kills the sign, so try a number and it's negative. F of minus 2 is 4, and f of 2 is also 4. 2 different inputs, 1 output. Step 3. The test fails, so stop. The function is not 1 to 1, and that alone rules out an inverse. Step 4. See exactly what breaks. If f inverse existed, what would f inverse of 4 return? Minus 2 or 2. It cannot choose, so it is not a function. So x squared on the real numbers has no inverse. Composition means chaining 2 functions together. Suppose g goes from A to b, and f goes from b to c. The composition f circle g is a new function from a to c. Read it from the inside out. First apply g to x, which lands in b, then apply f to that result, which lands in c in symbols. F circle g of x equals f of g of x. Watch the order carefully. The function written on the right, g, runs first. In the picture, a goes to g of a by the function g, then g of a goes to f of g of a by the function f. The dashed arrow is the whole trip in one hop, and that is the composition. Now a concrete example with small sets. The left picture does the 2 steps in a row. First g sends it to y, b to w, c to x, and d to w, then f sends v to I, w to h, x to I, and y to j. Now trace each starting element all the way through. Start with a. G sends it to y, then f sends y to j, so it ends at j. Start with b. G sends b to w, then f sends w to h, so b ends at h, then c goes to x, and on to I, and d goes to w, and on to h. The right picture shows exactly these 4 results. A to j, b to h, c to I, and d to h. That single picture is the composition f circle g. Let us compute a composition with formulas. Take f of x equals x squared, and g of x equals 2x plus 1. We start on the left with f of g of x. Step 1. The inner function runs first, and g of x is 2x plus 1, so we have f of the quantity 2x plus 1. Step 2. Now apply f, which squares its input. We get the quantity 2x plus 1 all squared. Now the right side, g of f of x. Step 3. This time f runs first, and f of x is x squared, so we have g of x squared. Step 4. Now apply g, which doubles its input and adds 1. We get 2x squared plus 1. Compare the two answers. The quantity 2x plus 1 squared is not the same as 2x squared plus 1. So f circle g is different from g circle f. Composition is not commutative, and the order changes the result. Now an example with finite sets. The function g maps the set of b, c to itself. G of it is b, g of b is c, and g of c is a. The function f maps of b, c to numbers. F of it is 3, f of b is 2, and f of c is 1. The rule on the first line says, run g first, then f. Take the input a, g sends it to b, then f sends b to 2. So f circle g of it is 2. Take the input b, g sends b to c, then f sends c to 1. So f circle g of b is 1. Take the input c, g sends c to a, then f sends it to 3. So f circle g of c is 3. There is a second question hiding here. Can we also form g circle f? Let us check it properly instead of guessing. Step 1. In g circle f, the function written on the right runs first, so f runs first. Step 2. What does f hand on? Its outputs are the numbers 1, 2, and 3. Step 3. What will g accept? Its domain is the letters of b and c. Step 4. Is the set 1, 2, 3 inside the set of b, c? No, they share nothing. So g is handed a number it cannot act on. That means g circle f is not defined here. The habit to build. Before you compose two functions, check that the outputs of the inner one are legal inputs to the outer one. One more composition, this time with integer formulas. Let f of x equal 2x plus 3, and let g of x equal 3x plus 2. We do f circle g here, and g circle f on the next slide. Step 1. In f circle g, the inner function g runs first. G of x is 3x plus 2, so we have f of the quantity 3x plus 2. Step 2. Now apply f, it doubles its input and adds 3. That gives 2 times the quantity 3x plus 2 plus 3. Step 3. Multiply out. 2 times 3x is 6x, and 2 times 2 is 4. So we have 6x plus 4 plus 3, which is 6x plus 7. Now the other order, g circle f, with the same two functions. Step 1. This time f runs first. F of x is 2x plus 3, so we have g of the quantity 2x plus 3. Step 2. Now apply g, it triples its input and adds 2. That gives 3 times the quantity 2x plus 3 plus 2. Step 3. Multiply out. 3 times 2x is 6x, and 3 times 3 is 9. So we have 6x plus 9 plus 2, which is 6x plus 11. Compare the two answers, 6x plus 7 and 6x plus 11. They differ by 4 for every x, so once more, f circle g is not the same as g circle f. The graph of a function is the collection of its input-output pairs. If f goes from a to b, its graph is the set of all ordered pairs a comma b, where a is in a and f of a equals b. When the domain is the integers, the graph is not a smooth line. It is a set of separate dots, one dot for each integer input. The left picture graphs f of n equals 2n plus 1. As n steps through the integers, the output climbs in steps. The dots lie on a straight slope, but only at whole number inputs. The right picture graphs f of x equals x squared. It gives the pairs minus 3, 9, minus 2, 4, minus 1, 1, 0, 0, and so on. The dots form the familiar bowl shape of a parabola, again only at integer inputs. Two functions appear again and again in computer science: floor and ceiling. The floor of x, written with two corner brackets that point up, is the largest integer that is less than or equal to x in plain words, round down to the nearest whole number. The ceiling of x, written with two corner brackets that point down, is the smallest integer that is greater than or equal to x in plain words, round up. Look at the examples. Ceiling of 3.5 is 4, because 4 is the smallest whole number not below 3.5. Floor of 3.5 is 3. Now the tricky part, negative numbers. Floor of minus 1.5 is minus 2, because we round down toward more negative. Ceiling of minus 1.5 is minus 1, because we round up toward 0. Always remember, floor goes down, ceiling goes up, even for negative values. Now the pictures of floor and ceiling. Both are step functions. The value stays flat across each interval of length 1, and then it jumps up by 1 to the next level. The left picture is the floor function. On each step the left end is a filled dot, meaning that point is included, and the right end is an open dot, meaning that point is left out. For example, between 1 and 2 the value is 1, including 1 but not 2. Then it jumps to 2. The right picture is the ceiling function, and it is the opposite. The left end of each step is open and the right end is filled. So between 1 and 2 the value is 2, not including 1 but including 2. A filled dot means the point belongs to the graph. An open dot means it does not. This table collects the properties of floor and ceiling you will use most often. In every line, n is any integer and x is any real number. 1a the floor of x equals n exactly when n is less than or equal to x, and x is below n plus 1. So n is the whole number just at or below x. 1b the ceiling of x equals n exactly when x is above n minus 1, and at most n. 1c says the same fact as 1a, rearranged so that n sits in the middle. And 1d does the same for the ceiling. Property 2 is a useful sandwich. X minus 1 is below the floor of x, the floor is at most xx is at most the ceiling, and the ceiling is below x plus 1. So both are always within 1 of x, the rest of the table is on the next slide. Now the rest of the table. Group 3 connects the two functions through negatives. 3a the floor of minus x equals minus the ceiling of x. 3b the ceiling of minus x equals minus the floor of x in plain words. Flipping the sign swaps floor and ceiling. That makes sense, because reflecting the number line turns rounding down into rounding up. Group 4 is about adding a whole number. 4a the floor of x plus n equals the floor of x plus n. 4b says the same for the ceiling. In plain words, a whole number may be pulled straight out of the brackets, because it never changes the fractional part. Now let us prove a fact about the floor function. Remember, the floor of a number is the largest integer that is less than or equal to it. We want to prove that the floor of 2x equals the floor of x plus the floor of x plus 1/2. Step 1. Split x into two parts. Write x as n plus epsilon, where n is a whole number and epsilon is the leftover, sitting from 0 up to but not including 1. Step 2. Read off the easy floor straight away. The floor of x is just n. Step 3. Ask what the answer depends on. Doubling x doubles epsilon, so everything turns on whether epsilon is small or large. Step 4. So we split into two cases at the halfway point. Either epsilon is below 1/2 or it is 1/2 or more. We work the first case next. Case 1. Epsilon is below 1/2. Work the left side first, which is the floor of 2x. Step 1. Put in x equals n plus epsilon, so it becomes the floor of 2n plus 2 epsilon. Step 2. 2n is already a whole number, and because epsilon is below 1/2, 2 epsilon sits from 0 up to but not including 1, so the floor is 2n. Now the second term on the right side, we want the floor of x plus 1/2. Step 3. Put in x equals n plus epsilon again. That gives the floor of n plus the quantity 1/2 plus epsilon. Step 4. Epsilon is below 1/2, so 1/2 plus epsilon is still below 1. The floor is therefore n. Finally add up the right side. The floor of x is n, and the floor of x plus 1/2 is n together, that is 2n, which matches the left side. Case 1 holds. Case 2. Epsilon is 1/2 or more. Work the left side first, the floor of 2x. Step 1. Put in x equals n plus epsilon. That gives the floor of 2n plus 2 epsilon. Step 2. Now 2 epsilon is at least 1, so it is no longer a leftover. Pull one whole unit out and write it as 2n plus 1, plus the quantity 2 epsilon minus 1. Step 3. That leftover 2 epsilon minus 1 sits from 0 up to but not including 1 because epsilon is below 1, so the floor is 2n plus 1. Now the second term. We want the floor of x plus 1/2. Step 4. That is n plus 1/2 plus epsilon. Since epsilon is at least 1/2, the fraction part is at least 1, so pull one more unit out. We get n plus 1 plus the quantity epsilon minus 1/2. Step 5. That last piece sits from 0 up to but not including 1/2, so the floor is n plus 1. Let us put the two cases side by side and finish. Case 1, epsilon below 1/2. The left side came out as 2n, the right side was n plus n, which is also 2n, they agree. Case 2, epsilon 1/2 or more. The left side came out as 2n plus 1. The right side was n plus 1, which is also 2n plus 1. They agree again. Now the last step of any case proof. Ask whether the cases cover everything. The leftover epsilon always sits from 0 up to 1, so it is either below 1/2 or it is not. There is no third possibility, so the identity holds for every real number x, and the small black square marks the end of the proof. This slide defines the factorial function. Factorial of n, written as n with an exclamation mark, means multiply together all the whole numbers from 1 up to n. One special rule. 0 factorial is defined to be 1, not 0. Now work the examples out. 1 factorial has a single factor, so it is 1. 2 factorial is 1 times 2, which is 2. 6 factorial multiplies 1, 2, 3, 4, 5, and 6. Take it in steps. 1 times 2 is 2, times 3 is 6, times 4 is 24, times 5 is 120, times 6 is 720. And 20 factorial is already about 2.4 times 10 to the power 18. Factorials grow extremely fast, which is why we want an estimate for them. 20 factorial was already huge, and we do not want to multiply out 100 factors by hand. The Stirling formula gives a close estimate instead. It says n factorial is about the square root of 2 pi n times the quantity n over e, raised to the power n. Now the wavy symbol between the two sides. It has a precise meaning. We write f of n wavy g of n when the limit, as n grows without bound, of f of n divided by g of n equals 1. Read that in plain words. Divide one side by the other. As n gets larger, that ratio settles down to 1. So the two sides may differ, but the difference stops mattering as n grows. Section 2.4. Sequences and Summations. We now turn to sequences, which are ordered lists of numbers or objects, and to compact ways of adding their terms up. Let us look at the plan for this section. First, sequences, what they are and how we write them. Two important families serve as our examples, the geometric progression and the arithmetic progression. Second, recurrence relations, which describe a sequence by saying how each term depends on earlier terms. The Fibonacci sequence is the classic example. And third, summations, which are compact ways to add up the terms of a sequence. Use this list as a map for the section. Let us begin with the idea. A sequence is an ordered list of elements. Ordered means the position matters. The first term, the second term, the third term, and so on. Look at the two examples. The first list is 1, 2, 3, 5, 8. The second list is 1, 3, 9, 27, 81, and it continues. Sequences appear everywhere, not only in mathematics and computer science, but in many other fields, from the growth patterns of plants to rhythm and structure in music. In this section, we build the language we need to write sequences clearly, and to write the sum of their terms in a compact way. Now the careful definition. A sequence is really a function in disguise. Its inputs are integers, usually the whole number starting at 0 or starting at 1. The output can be anything, an element of some set S. Instead of writing f of n for the output at position n, we use a special notation. The letter O with a small n written below it, read as a sub n. So a sub n is just another name for f of n. It is the value that sits at position n in the list. We call a sub n a term of the sequence. So the first term, the second term, and so on are each in a sub n for a particular n. Now a concrete example of a sequence. We use curly braces around a sub n to name the whole sequence at once. The rule is a sub n equals 1 over n, so to get any term, we take 1 divided by its position number. Let us write out the first few terms. The first term is 1 over 1, which is 1. The second term is 1 over 2, 1/2. The third term is 1 over 3, 1/3. The fourth term is 1 over 4, 1/4. So the list is 1, 1/2, 1/3, 1/4, and it keeps going, with the terms getting smaller and smaller. A geometric progression is a sequence where you get each term by multiplying the one before it by a fixed number. That fixed number is called the common ratio, written R. The starting value is called the initial term, written A, so the sequence is a, then a times R, then a times R squared, then a times r cubed, and in general a times r to the power n. Let us look at 3 examples. In the first, a is 1 and r is minus 1. Multiplying by minus 1 each time just flips the sign, so we get 1 minus 1, 1 minus 1, alternating forever. In the second, a is 2 and r is 5. Each term is 5 times the last. 2, 10, 50, 250, 1250. In the third, a is 6 and r is 1/3. Each term is 1/3 of the last, so the numbers shrink. 6, 2, 2/3, 2/9, 2/27. An arithmetic progression is similar in spirit, but instead of multiplying, we add. Each term is the one before it plus a fixed number. That fixed number is called the common difference, written d. The starting value is again the initial term. So the sequence is a, then a plus d, then a plus 2d, and in general a plus n times d. Look at the 3 examples. In the first, a is minus 1 and d is 4. Adding 4 each time gives minus 1, 3, 7, 11, 15. In the second, a is 7 and d is minus 3. Subtracting 3 each time gives 7, 4, 1, minus 2, minus 5. In the third, a is 1 and d is 2, which gives the odd numbers 1, 3, 5, 7, 9. Let us make the difference between the 2 families sharp, because they are easy to mix up. A geometric progression multiplies. Each term is the one before it, times the ratio r, so the sequence is a r squared, and so on. To test it, divide each term by the one before it. If you always get the same number, it is geometric, and that number is r. An arithmetic progression adds. Each term is the one before it plus the difference d to test it. Subtract instead. If the gap between neighbors is always the same, it is arithmetic, and that gap is d. One caution before you divide. The term you divide by must not be 0. If a term is 0, as in the sequence 0, 0, 0, the ratio test says nothing and you go back to the definition instead. This slide connects sequences to computer science through the idea of a string. A string is a finite sequence of characters, taken from a fixed, finite collection of symbols that we call an alphabet. Because it is a sequence, the order of the characters matters. Strings are everywhere in computer science. Text is a sequence of characters, and data is a sequence of bits, that is, zeros and ones. There is a special string with no characters at all, called the empty string, and we write it with the Greek letter lambda. The number of characters in a string is called its length. For example, the string of B, C, D, E has 5 characters, so its length is 5. This slide introduces recurrence relations, one of the most useful ideas about sequences. A recurrence relation is an equation that defines a term of a sequence using earlier terms. So instead of a direct formula for a sub n, we get a rule that says, to find a sub n, look back at some of the terms before it. This rule holds for all n from some starting point onward. We say a sequence is a solution of the recurrence relation if all of its terms actually obey the equation. But a recurrence alone is not enough to pin down the sequence, because we still need somewhere to start. That is what the initial conditions do. They give the first term or the first few terms before the recurrence takes over. Together, the initial conditions plus the recurrence relation determine the whole sequence. In example 1, the rule is a sub n equals a sub n minus 1 plus 3. In words, each term is the term just before it plus 3. The initial condition is a sub 0 equals 2. So we build the sequence one step at a time. A sub 1 equals a sub 0 plus 3, which is 2 plus 3, which is 5. A sub 2 equals a sub 1 plus 3, which is 5 plus 3, which is 8. A sub 3 equals a sub 2 plus 3, which is 8 plus 3, which is 11. Watch how each answer feeds into the next line. Example 2 has a different rule. A sub n equals a sub n minus 1 minus a sub n minus 2. In words, each term is the previous term minus the one before that. Because this rule looks back 2 steps, one starting value is not enough. We need 2 initial conditions. A sub 0 equals 3 and a sub 1 equals 5. Now we compute. A sub 2 equals a sub 1 minus a sub 0, which is 5 minus 3, which is 2. A sub 3 equals a sub 2 minus a sub 1, which is 2 minus 5, which is minus 3. So an answer can go negative. The key idea: how far back the rule reaches tells you how many starting values you must be given. The Fibonacci sequence is the most famous recurrence in mathematics. It has 2 initial conditions. F sub 0 equals 0 and F sub 1 equals 1. The rule is that each new term is the sum of the 2 terms before it. Let us build it. F sub 2 is F sub 1 plus F sub 0, which is 1 plus 0, which is 1. F sub 3 is F sub 2 plus F sub 1, which is 1 plus 1, which is 2. F sub 4 is F sub 3 plus F sub 2, which is 2 plus 1, which is 3. F sub 5 is F sub 4 plus F sub 3, which is 3 plus 2, which is 5. F sub 6 is F sub 5 plus F sub 4, which is 5 plus 3, which is 8. So the sequence begins 0, 1, 1, 2, 3, 5, 8, and it keeps growing this way. So far we have computed terms one by one, but often we want a direct formula, one that gives a sub n straight from n, with no chain of earlier terms. Finding such a formula is called solving the recurrence relation, and the formula itself is called a closed formula. Instead of adding 3 over and over, we would like a single expression in n. The full theory of solving recurrences waits until Chapter 8. For now, we use a simple, hands-on method called iteration. We unfold the recurrence step by step, watch for a pattern, and then guess the formula. A guess is not yet a proof. Later, in Chapter 5, the method of mathematical induction lets us prove such a guess is correct. Now the first way to do iteration, called forward substitution or working upward. We start at the bottom. From the known first term, a sub 1 equals 2, and climb up. A sub 2 equals 2 plus 3. Watch this. We do not add the numbers up yet. A sub 3 equals the previous value, 2 plus 3, plus another 3, which we write as 2 plus 3 times 2. A sub 4 becomes 2 plus 3 times 3. We keep the shape 2 plus 3 times something, because that shape is the pattern. Do you see it? The multiplier of 3 is always 1 less than the position. So for a sub n, the multiplier of 3 is n minus 1. That gives a sub n equals 2 plus 3 times, open bracket, n minus 1, close bracket. That is our closed formula. Now the second way, called backward substitution, or working downward. This time we start at the top with a sub n and go down. A sub n equals a sub n minus 1 plus 3. Step 1. Replace a sub n minus 1 using the same rule. It equals a sub n minus 2 plus 3. So a sub n equals a sub n minus 2 plus 3 times 2. Step 2. Repeat. A sub n equals a sub n minus 3 plus 3 times 3. Again, we keep the pattern visible instead of adding. Keep peeling one step at a time. After enough steps, we reach a sub 1. Substituting a sub 1 equals 2 gives 2 plus 3 times n minus 1. That is exactly the same closed formula as before. Forward and backward substitution are two roads to the same answer. Let us put the two methods side by side. Forward substitution starts from the known first term. A sub 1 equals 2 and climbs upward. It gave a sub n equals 2 plus 3 times n minus 1. Backward substitution starts from the general term a sub n and peels downward until it reaches a sub 1. It gave exactly the same formula. Two different roads, one answer. And now the habit worth keeping. Always test a closed formula on a term you already know. Put an equal to 1. 3 times 0 is 0, so we get 2. And a sub 1 was given as 2. It checks out. Let us model money in a bank account. A person puts $10,000 into a savings account. Each year the bank adds 11% interest, compounded annually. That means the interest is added once per year, and then itself earns interest next year. We want the balance after 30 years. Let P sub n be the amount after n years. In 1 year, the new balance is the old balance plus 11% of the old balance. That is P sub n equals P sub n minus 1 plus 0.11 times P sub n minus 1. We can factor this. It equals 1.11 times P sub n minus 1. The starting amount is P sub 0 equals 10,000. The key idea. Adding 11% is the same as multiplying by 1.11. Now we solve the recurrence by forward substitution. Watch the count of factors. After 1 year, P sub 1 is 1.11 times P sub 0. That is one factor. After 2 years, P sub 2 is 1.11 times P sub 1. Substituting P sub 1, that is 1.11 squared times P sub 0. Two factors. After 3 years, we bring in a third factor, so P sub 3 is 1.11 cubed times P sub 0. The pattern is clear now, so we can jump to the general term. After n years, we have multiplied by 1.11 exactly n times. So P sub n is 1.11 to the power n times P sub 0, which is 1.11 to the power n times 10,000. Chapter 5 proves this properly by induction. We have the closed formula, so now we answer the question that was actually asked. It asked for the balance after 30 years. Step 1. Take the formula and substitute n equal to 30. Step 2. That gives 1.11 to the power 30 times 10,000. The power of 30 is just the growth factor of 1.11 applied 30 times over. Step 3. Work that out. The balance is $228,922.97. Look at what that means. 11% a year, left alone for 30 years, turns $10,000 into more than $228,000. That is over 22 times the money that was paid in. This is the power of compounding. Sometimes we are given only the first few numbers of a sequence and asked to find a rule that fits. This is detective work, and this checklist guides the guessing. First, are any values repeated? Second, can you get from one term to the next by always adding the same amount, which suggests an arithmetic sequence, or by always multiplying by the same amount, which suggests a geometric one. Third is each term built by combining two or more earlier terms, like Fibonacci. Fourth, do the term cycle, repeating in a fixed pattern. Fifth, do the numbers match a famous sequence you already know, such as the squares or the powers of 2. Run through this list, and a pattern often jumps out. Let us try the checklist on 3 examples. Example 1. 1, 1/2, 1/4, 1/8, 1/16. The denominators are 1, 2, 4, 8, 16, which are powers of 2. So a good guess is a sub n equals 1 over 2 to the power, and this is a geometric progression with ratio 1/2. Example 2. 1, 3, 5, 7, 9. Each term is the previous plus 2. So a good guess is a sub n equals 2n plus 1. This is an arithmetic progression with common difference 2. Example 3. 1 minus 1, 1 minus 1, 1. The sign flips each time. A good guess is a sub n equals minus 1 to the power n. This is a geometric progression with ratio minus 1. This table lists sequences you will meet again and again, so it is worth knowing them by sight. The first row is n squared, 1, 4, 9, 16, and so on, the perfect squares. The second row is n cubed, 1, 8, 27, 64. The third row is n to the fourth power, 1, 16, 81, 256. The fourth row is 2 to the power n, 2, 4, 8, 16, doubling each time. The fifth row is 3 to the power n, 3, 9, 27, 81, tripling each time. The sixth row is n factorial, 1, 2, 6, 24, 120, and it grows extremely fast. The last row holds the Fibonacci numbers, where each term is the sum of the 2 before it. Watch how much faster factorial, and the powers grow than a polynomial row like n squared. Now a harder guess that uses the table of useful sequences. We are given 10 terms, 1, 7, 25, 79, and so on. Step 1. Divide each term by the one before it. 7 over 1 is 7. 25 over 7 is about 3.5. 79 over 25 is a little over 3. The ratios settle down close to 3. Step 2. A ratio near 3 points at the powers of 3. 3, 9, 27, 81. Step 3. Now line the two lists up. Our terms are 1, 7, 25, 79. The powers are 3, 9, 27, 81. Step 4. Subtract column by column. 3 minus 1 is 2, 9 minus 7 is 2, 27 minus 25 is 2, 81 minus 79 is 2. The gap is always 2. Step 5. So the conjecture is a sub n equals 3 to the power n minus 2, and always test a conjecture. 3 to the fourth is 81, minus 2 is 79, which matches the fourth term. It fits. Now we meet a very compact way to write a long sum. Suppose we have a list of terms, a sub m plus 1, and so on up to a sub n. To add them all together, we use the big Greek capital letter sigma, which looks like a pointy e. You read it as the sum. Under the sigma, we write j equals m, that is the starting value, called the lower limit. Above the sigma, we write n, the ending value, called the upper limit. The 3 forms on the slide are different ways to write the same sum. Each one means add a sub m plus a sub m plus 1 plus ... plus a sub n. The letter j here is called the index of summation. Think of it as a counter that steps through every whole number from m up to n, picking out each term to add. the index does not have to run through a straight range like m to n. We can also add over the elements of a set. The notation sigma with j and s means add the term a sub j for every j that belongs to the set S. Line 1. R to the 0 plus R to the 1 plus R squared plus R cubed, and so on up to R to the n. The index runs from 0 to n, so we write the sum from j equals 0 to n of R to the j. Line 2. 1 plus 1/2 plus 1/3 plus 1/4 going on forever. The index starts at 1 and never stops, so we write the sum from I equals 1 to infinity of 1 over I infinity on top, means the sum never ends. Line 3. A sub 2 plus a sub 5 plus a sub 7 plus a sub 10. These indexes do not form a range, so we name the set instead. Let S be 2, 5, 7, and 10. Then we write the sum over j in S of a sub j. A geometric series is a special, very common kind of sum. Each term is the one before it multiplied by a fixed number r, called the common ratio. So the terms are a, then a times r, then a times r squared, and so on. The sum has a short answer, which we call a closed form, and there are two cases. If r is not equal to 1, the whole sum equals a times r to the n plus 1, minus a, all divided by r minus 1. If r equals 1, every term is just a, and there are n plus 1 of them, so the sum is simply n plus 1 times a. The big win here is speed. Instead of adding many terms one at a time, a single formula gives you the answer. Let us prove that closed form formula for the case where r is not 1. Step 1. Give the sum a name. Call it S sub n. The sum from j equals 0 to n of a times r to the j. Step 2. And this is the whole trick. Multiply both sides by r on the left. We get r times S sub n on the right, r times the sum. Step 3. Move the r inside the sum. Multiplying r to the j by one more r adds 1 to the exponent. That gives the sum from j equals 0 to n of a times r to the j plus 1. We continue on the next slide. We pick up from r times S sub n equals the sum from j equals 0 to n of a times r to the j plus 1. Step 1. Shift the index to tidy the exponent. Let k equal j plus 1. When j was 0, k is 1. When j was n, k is n plus 1. So the sum now runs from k equals 1 to n plus 1 of a times r to the k. Step 2. We want the range to match the original sum, which ran from 0 to n, so remove the top term at k equals n plus 1, which is a times r to the n plus 1, and add in the missing bottom term at k equals 0, which is a. Step 3. Look at that first sum. It runs from 0 to n of a times r to the k, and that is exactly S sub n, so r times S sub m equals S sub n, plus a r to the n plus 1, minus a. Now we can solve for S sub n. We now have an ordinary equation, and S sub n is the unknown. Line 1 is what we reached. R times S sub n equals S sub n, plus the quantity a r to the n plus 1, minus a. Step 1. Move S sub n across to the left. That gives r times S sub n minus S sub n equals a r to the n plus 1 minus a. Step 2. Factor S sub n out of the left side. That gives S sub n times the quantity r minus 1. Step 3. Divide both sides by r minus 1. So S sub n equals a r to the n plus 1 minus a all over r minus 1. One condition, and it matters. We divided by r minus 1, so this needs r not equal to 1. What if r is 1? Then every term of the sum is just a, and there are n plus 1 terms, so the sum is n plus 1 times a. This table collects the summation formulas you will use most often, so keep it handy. The first row is the geometric series we just proved. The sum from k equals 0 to n of a times r to the k equals a times r to the n plus 1, minus a over r minus 1, when r is not 1. The next three rows are sums of powers of the counting numbers. The sum of k from 1 to n is n times n plus 1 over 2. The sum of k squared is n times n plus 1 times 2n plus 1 over 6. The sum of k cubed is n squared times n plus 1 squared over 4. We prove these three later using mathematical induction. The last two rows are infinite sums that only work when the absolute value of x is below 1. The sum of x to the k from 0 to infinity is 1 over 1 minus x. And the sum of k times x to the k minus 1 is 1 over the quantity 1 minus x squared. These last two are proved in the textbook using calculus. Section 2.5, Cardinality of Sets. So far, cardinality has just meant counting the elements of a finite set. Now we learn how to compare the sizes of sets, even infinite ones. Let us look at the plan for this section. First, cardinality, a precise way to say when two sets have the same size using functions. And second, countable sets, which infinite sets are small enough to be listed one by one. Use this short list as our roadmap. Now the big new idea. To compare the sizes of two sets, we use functions instead of counting. Two sets A and B have equal cardinality if, and only if there is a one-to-one correspondence between them. A one-to-one correspondence is also called a bijection. It pairs every element of A with exactly one element of B, and nothing is left over on either side. Next, suppose there is only a one-to-one function, also called an injection. From A into B, different elements of A always go to different elements of B. Then A is no bigger than B, and we write the size of A is less than or equal to the size of B. Finally, if A is no bigger than B, but the two sets do not have the same cardinality, then A is strictly smaller. We write the size of A is less than the size of B. What makes this powerful is that it works even for infinite sets, where plain counting is impossible. Now we can classify infinite sets. A set is called countable if it is either finite, or it has the same cardinality as the positive integers. In plain words, a countable set is one whose elements you could line up in a list and count off, even if the list never ends. A set that is not countable is called uncountable. A key example, the set of real numbers, all the numbers on the number line, is uncountable. It is simply too big to list. When an infinite set is countable, we give its size a special name. We write its cardinality as Aleph, with a small zero below it. Aleph is the first letter of the Hebrew alphabet, and it looks a bit like a slanted X. We read it as Aleph null. This is our first infinite cardinal number. An infinite set is countable if, and only if we can put its elements in a list. The list is a sequence. A first element, a second element, a third element, and so on, one for each positive integer. Now the key point. Saying there is a one-to-one correspondence from the positive integers to the set S is exactly the same as writing S as a sequence of 1, a 2, a 3, and so on, where a 1 is f of 1, a 2 is f of 2, and in general a n is f of n. So from now on, to show a set is countable, we just need to find a way to list all of its elements, with nothing missing and nothing counted twice. This is a famous story from the mathematician David Hilbert. Imagine a hotel with a countably infinite number of rooms. Room 1, room 2, room 3, and so on forever. Every single room is already full. Now one more guest walks in. In a normal hotel with a fixed number of rooms, this is impossible. But here we can do it, because the rooms are countable and so they can be listed. Now the move. Ask the guest in room 1 to go to room 2. Ask the guest in room 2 to go to room 3. In general, the guest in room N moves to room N plus 1. After everyone moves, room 1 is empty, so the new guest takes it, and every old guest still has a room of their own. Nobody was turned out. And we can do more than seat one guest. With a similar idea, we can make room for a countable number of new guests all at the same time. And we can go further still. Imagine a countable number of buses pull up, and each bus itself carries a countable number of guests. Even then, everyone can be seated. The exercises walk you through how. Now the lesson to take away. For an infinite set, the words already full do not mean no room. You can add to such a set and still line it up, one for one, with the counting numbers. Infinity behaves in ways that everyday intuition does not prepare you for. Let us prove that the set of positive even numbers is countable. Remember what we need, a perfect pairing with the counting numbers. Step 1. Propose a pairing. Try f of n equals 2n. The top row of the table holds the counting numbers 1, 2, 3, 4, 5, 6. Underneath each one sits its double, 2, 4, 6, 8, 10, 12. Step 2. Check 1 to 1. Suppose f of n equals f of m, then 2n equals 2m. Divide both sides by 2, and we get n equals m, so different inputs never share an output. Step 3. Check onto. Take any positive even number t being even. It can be written as 2 times k for some positive integer k, then f of k equals t, so no even number is missed. Step 4. Both checks passed, so f is a bijection. The positive even numbers are countable. Now the full set of integers. It has negative numbers, 0, and positive numbers. Step 1. See the problem first. The integers run off in both directions, so there is no obvious place to start the list. Step 2. Fix that by starting in the middle at 0. Step 3. Now weave. Take 1, then minus 1, then 2, then minus 2, then 3, then minus 3, and keep going. Step 4. Check the list is complete. Take any integer k. Does it ever arrive? Yes, and we can say exactly when. A positive k arrives at step 2k, so 1 is second and 2 is fourth. 0 and the negatives arrive at step 2 times the size of k plus 1, so 0 is first and minus 3 is seventh. Every integer is reached after a finite wait, and none is written twice. So the list matches the integers with the counting numbers, one for one. The integers are countable. This is the same weaving rule, written as a formula instead of a picture. The inputs n are the counting numbers 1, 2, 3, and so on. Read the two cases. When n is even, f of n is n divided by 2. Having an even number gives a whole number, so n equals 2 gives 1, n equals 4 gives 2, and n equals 6 gives 3. The even inputs walk out to the right. When n is odd, f of n is minus, in brackets n minus 1 divided by 2. So n equals 1 gives 0, n equals 3 gives -1, and n equals 5 gives -2. The odd inputs give 0 first, then walk out to the left. So the even inputs cover the positive integers, and the odd inputs cover 0 and the negatives. Between them, they reach every integer exactly once, which is what countable means. Now a harder and more surprising case, the positive fractions. First, the definition. A rational number is one you can write as a ratio, p over q, where p and q are integers and q is not 0. For example, 3/4 is rational. The square root of 2 is not. Between any two fractions, there are infinitely many more, so it feels like there are far too many to list. Yet we can still list them all in one sequence R1, R2, R3, and so on. The clever idea is to place every fraction p over q in a big grid, and then walk through the grid along diagonal lines. On each diagonal, the sum p plus q stays the same. The next slide shows exactly how the walk goes. Look at the grid. Along the top, the numerator p grows, 1, 2, 3, and so on. Going down, the denominator q grows the same way. So the fraction in column p and row q is simply p over q. Now we walk the grid along diagonal lines. On each diagonal, the sum of the numerator and the denominator is the same. We start with that sum equal to 2, then 3, then 4, and so on, following the blue arrows back and forth. Some fractions equal a value we have already written down. For example, 2 over 2 is just 1, which we already listed, so we skip it. Those skipped ones are left uncircled. The circled ones give us the list. 1, then 1/2, then 2, then 3, then 1/3, then 1/4, then 2/3, and so on. Every positive fraction appears exactly once, so the positive rationals are countable. Next, strings. A string is a finite row of symbols taken from a fixed alphabet A, for example, the letters A through Z. We want to show that the set of all finite strings is countably infinite. First, we agree on an alphabetical order of the symbols, like in a dictionary. Then we list the strings by length, shortest first. We start with all strings of length 0, which is just the empty string. Then all strings of length 1, in dictionary order. Then all strings of length 2, in dictionary order. And we keep going. The important point is that for each fixed length there are only finitely many strings, so we never get stuck on one length forever. That gives a single list of all strings, so the set of strings is countably infinite. Now a computer science example, the set of all Java programs. This sounds enormous, but it is still only countable. Every Java program is, in the end, just a finite string of characters. From example 4, we already know how to list all finite strings in one sequence, so we go through that list of strings one at a time. For each string, we feed it into a Java compiler. A compiler can check whether the string is a correct Java program or just nonsense. If the compiler says yes, this is a valid program, we add it to our list of programs. If not, we skip it and move to the next string. Walking through all strings this way produces a list of every Java program, so the set of all Java programs is countable. Now the big surprise. The real numbers are not countable. There are, in a precise sense, more real numbers than counting numbers. The method is due to George Cantor and is called the diagonalization argument. It is a proof by contradiction, so we begin by assuming the opposite of what we want. Step 1. Suppose the reals are countable. Then the real numbers between 0 and 1 are also countable, because any part of a countable set is countable. Step 2. Being countable, we can list all of them in order: R1, R2, R3, and so on. Step 3. We write each of these numbers in its decimal form. Then, on the next slide, we look down the diagonal of this list and build a new number that cannot be anywhere on it. That is the contradiction, and it tells us the reals cannot be listed at all. This is the heart of the argument. We assume the numbers between 0 and 1 can be listed, so let us write that list out as decimals. Line 1. The first number, R1, has digits D11, D12, D13, and so on after the decimal point. Its first digit is highlighted. Line 2. The second number, R2, has digits D21, D22, and so on. This time the second digit is highlighted. Line 3. The third number highlights its third digit, D33. Line 4. The fourth number highlights its fourth digit, D44. And the list goes on forever. The rule for the labels is simple. Dij is the jth digit of the ith number. The highlighted cells run down the diagonal of the table. On the next slide, we use just those diagonal digits. Now we build the number that breaks the list. Step 1. Ignore everything except the highlighted diagonal. Read off D11, D22, D33, and so on. Step 2. Make a new digit for each one chosen to disagree. If the diagonal digit is not 3, our digit is 3. If the diagonal digit is already 3, our digit is 4. Either way, our digit differs from the one we read. Step 3. Glue the new digits together into one number. Call it R, written 0.R1, R2, R3, and so on. Step 4. Now compare R with any line of the list. Say line I by the way we chose digit I. They differ in that digit. So R is not equal to Ri. Step 5. That holds for every line, so R is nowhere on the list. But R is a real number between 0 and 1, so it should have been there. That is the contradiction. The lesson is general. Whatever list you offer, this recipe builds a number you missed. So no complete list exists, and the reals are uncountable. Section 2.6. Matrices. A matrix is a rectangular arrangement of numbers in rows and columns. We will learn what a matrix is and how to do arithmetic with matrices. Let us look at the plan for this section. First, we define exactly what a matrix is: its rows, its columns, and its entries. Second, matrix arithmetic: how to add matrices and how to multiply them. Third, the transpose of a matrix, which flips rows and columns, and powers of a matrix, which come from multiplying it by itself. And fourth, 0-1 matrices, whose entries are only zeros and ones, and which are very useful for representing relations and graphs. Welcome to matrices. A matrix is a table of numbers arranged in rows and columns. It is one of the most useful structures in discrete mathematics. Let us see why. First, matrices describe special functions called linear transformations. Second, a matrix can record which points of a graph are joined by an edge. We will use that idea a lot in Chapter 10. Later, we will also model transportation systems with matrices. And communication networks too. Many of the algorithms in this course rest on matrix models. So in this section, we learn just the matrix arithmetic that we will need. Take it slowly. Each idea is small, and they build on each other. Now the definition. A matrix is a rectangular array of numbers. If it has m rows and n columns, we call it an m by n matrix. We always say rows first, then columns. The plural of matrix is matrices. A matrix with the same number of rows and columns is called square. Two matrices count as equal only when three things match. The same number of rows, the same number of columns, and every matching entry the same. Look at the example. It has 3 rows and 2 columns, so it is a 3 by 2 matrix. Read the entries row by row, 1 and 1, then 0 and 2, then 1 and 3. Now we need names for the pieces. Take a general matrix A with m rows and n columns. Each entry carries 2 labels, and the order never changes. Row first, column second. So a sub ij means the entry in row I and column j. Say that to yourself every time you read a subscript, because swapping the 2 labels is the most common slip. On the next slide, we name the whole strips, the rows and the columns. Now the strips. The ith row of A is the whole horizontal strip, a sub I1, a sub I2, and so on to a sub In. Watch the labels. The first one stays at I and the second one runs. That strip is itself a matrix of size 1 by n. The jth column is the whole vertical strip, a sub 1j, a sub 2j, down to a sub mj. This time the second label stays at j and the first one runs. That strip is an m by 1 matrix. The single element, a sub ij, is called the ij entry of A. And there is a shorthand for the whole matrix. We write an equals square bracket a sub ij, which means the matrix whose ij entry is a sub ij. It saves drawing the whole grid every time. Adding matrices is the easy operation. It works entry by entry. Both matrices must be the same size, m by n. To find each entry of the sum, add the 2 entries that sit in the same position. So the ij entry of a plus b is a sub ij plus b sub ij. The example shows 2 3 by 3 matrices and their sum. We work the entries out one at a time on the next slide. One warning first. You can only add matrices of the same size. If the shapes differ, addition is not defined because some entry has no partner to add to. Let us work the entries out in reading order. Position row 1, column 1. The first matrix has 1 there and the second has 3. 1 plus 3 is 4. Position row 1, column 2, 0 and 4. 0 plus 4 is 4. Position row 1, column 3, minus 1 and minus 1. Adding 2 negatives gives minus 2. Now drop to row 2, column 1, 2 and 1. 2 plus 1 is 3. Row 2, column 2, 2 and minus 3. That gives minus 1. Carry on the same way through all 9 positions. There is nothing else to it. Same position, add the pair. Matrix multiplication is more involved, so go slowly. To multiply A by B, the inner sizes must match. A is m by k, and B must be k by n. The result is m by n. Each entry of the product is not one product but a sum of products. To get C sub ij, take the ith row of A and the jth column of B, multiply them position by position, then add all those products. In symbols, C sub ij is the sum over L from 1 to k of a sub I L times B sub Lj. The example is a 4 by 3 times a 3 by 2, so the answer is 4 by 2. We work its entries out on the next slide. One warning. If the columns of A do not match the rows of B, the product does not exist at all. Let us work 4 entries out so the rule sticks. Entry C11. Take row 1 of A, which is 1, 0, 4. Take column 1 of B, which is 2, 1, 3. Pair them up. 1 times 2 is 2, 0 times 1 is 0, 4 times 3 is 12. Add 2 plus 0 plus 12 is 14. Entry C12. Same row of A, but now column 2 of B, which is 4, 1, 0. 1 times 4 is 4, 0 times 1 is 0, 4 times 0 is 0. Add 4. Entry C21. Now row 2 of A, which is 2, 1, 1, against column 1 of B. 2 times 2 is 4, 1 times 1 is 1, 1 times 3 is 3. Add 8. Entry C41. Row 4 of A is 0, 2, 2, against column 1 of B. 0 times 2 is 0, 2 times 1 is 2, 2 times 3 is 6. Add 8. Every entry is found the same way. Pick its own row from A and its own column from B. One warning before we move on. A times B is undefined unless the columns of A match the rows of B, otherwise some number in the row would have no partner in the column. This picture shows the multiplication rule in one glance. The left matrix is A with one whole row marked in red, the ith row. Its entries are a sub I1, a sub I2, and so on to a sub Ik. The right matrix is B with one whole column marked in red, the jth column. Its entries are B sub 1j, B sub 2j, and so on down to B sub kj. Both red strips have the same length, k. That is exactly why the inner sizes must match. The next slide pairs them up. Now pair the two red strips up. To find the single entry C sub ij, shown in red inside the product, multiply the first row entry by the first column entry, then the second by the second, then the third by the third, and so on to the kth. Finally, add all those products together. Written out, C sub ij equals a sub I1 times B sub 1j, plus a sub I2 times B sub 2j, and so on, up to a sub Ik times B sub kj. Every entry of the product is found the same way. It picks its own row from A and its own column from B, and the red strips slide to that position. With ordinary numbers, 3 times 5 equals 5 times 3. With matrices, this is usually false, and order matters. Take it to be the 2 by 2 matrix with rows 1, 1 and 2, 1. Take B with rows 2, 1 and 1, 1. The question is whether a times B equals B times A. Do not guess. Let us follow a plan. First compute a times B entry by entry, then compute B times of the same way. Only then compare the two answers. We work them out over the next 2 slides. First, a times B rows come from A, columns from B. Position 1, 1. Row 1 of A is 1, 1. Column 1 of B is 2, 1. 1 times 2 is 2, 1 times 1 is 1. 2 plus 1 is 3. Position 1, 2. Row 1 of A again, but column 2 of B, which is 1, 1. 1 times 1 is 1, 1 times 1 is 1. That is 2. Position 2, 1. Row 2 of A is 2, 1. Column 1 of B is 2, 1. 2 times 2 is 4, 1 times 1 is 1. That is 5. Position 2, 2. Row 2 of A against column 2 of B. 2 times 1 is 2, 1 times 1 is 1. That is 3. Collect the 4 numbers into the matrix. A times B has rows 3, 2, and 5, 3. Now B times A, the roles swap. Rows come from B, columns from A. Position 1, 1. Row 1 of B is 2, 1. Column 1 of A is 1, 2. 2 times 1 is 2, 1 times 2 is 2. 2 plus 2 is 4. Position 1, 2. Row 1 of B against column 2 of A, which is 1, 1. 2 times 1 is 2, 1 times 1 is 1. That is 3. Position 2, 1. Row 2 of B is 1, 1. Column 1 of A is 1, 2. 1 times 1 is 1, 1 times 2 is 2. That is 3. Position 2, 2. Row 2 of B against column 2 of A, 1 times 1 is 1. 1 times 1 is 1. That is 2. Collect them. B times A has rows 4, 3, and 3, 2. Now compare. A times B was rows 3, 2, and 5, 3. B times it is rows 4, 3, and 3, 2. Every entry is different, so matrix multiplication is not commutative. Keep the factors in the order you are given. The identity matrix plays the role that the number 1 plays for ordinary multiplication. We call it I sub n, where n is its order, meaning it is n by n. Its entries are written delta sub ij. The rule is simple. Delta sub ij is 1 when I equals j, and 0 when I differs from j, so it has 1s going down the main diagonal and 0s everywhere else. Its special power is this. Multiplying any matrix A by the identity gives back a unchanged. In symbols, a times I sub n equals I sub m times A equals A. Because the identity behaves like 1, we can now define powers of a square matrix. A to the 0 is defined as the identity, and a to the r means a multiplied by itself r times. The last idea is the transpose. Take a matrix A that is m by n its transpose. Written A with a small t is the n by m matrix you get by turning rows into columns. The first row of A becomes the first column of the transpose. The second row becomes the second column, and so on. In symbols, if a transpose has entries B sub ij, then B sub ij equals a sub j. I watch the labels swap places. Look at the example. The original is 2 by 3, with rows 1, 2, 3, and 4, 5, 6. After transposing, it becomes 3 by 2. The first row, 1, 2, 3, stands up as the first column. The second row, 4, 5, 6, becomes the second column. So the answer has rows 1, 4, 2, 5, and 3, 6. This slide is about symmetric matrices. A square matrix A is called symmetric when it equals a transpose. Remember, the transpose flips the matrix over its main diagonal. The entry in row I, column J, trades places with the entry in row J. Column I, so A, is symmetric exactly when a sub ij equals a sub ji for every row I and every column J. Look at the example. The entry in row 1, column 2 is 1, and the entry in row 2, column 1 is also 1. The entry in row 2, column 3 is 1, and the entry in row 3, column 2 is also 1. Every pair matches. So when we take the transpose, nothing changes. A transpose equals A in short. A symmetric matrix is a reflection of itself across the main diagonal, and it does not change when you interchange its rows and columns. Now we meet 0-1 matrices. A 0-1 matrix is very simple. Every single entry is either 0 or 1. Nothing else is allowed. These matrices matter later, in chapters 9 and 10, where they represent things like relations and graphs. To compute with them, we use Boolean arithmetic, which is built from 2 operations on single bits. The first is the meet, written with a wedge that points up and read as and. B1 and B2 is 1 only when both B1 and B2 are 1, otherwise it is 0. The second is the join, written with a wedge that points down and read as or. B1 or B2 is 1 when at least one of them is 1. It is 0 only when both are 0. Remember these two little rules, because every operation on 0-1 matrices is built from them. Now the definitions of join and meet for two 0-1 matrices. Let A and B both be M by n 0-1 matrices. They must have the same number of rows and the same number of columns. The join of A and B, written with the down-pointing wedge, is a new 0-1 matrix. Its entry in row I, column J is a sub ij join B sub ij, so we apply the or rule to each matching pair of entries. The meet of A and B, written with the up-pointing wedge, is built the same way, but using the and rule. Its entry in row I, column J is a sub ij meet B sub ij. So both operations work entry by entry, comparing the two matrices cell against matching cell, and the answer has the same size as the inputs. Let us work the example. A and B are both 2 by 3 0-1 matrices. Take the join first, which uses or on each matching pair. Row 1, 1 or 0 is 1, 0 or 1 is 1, 1 or 0 is 1. So the top row of the answer is 1, 1, 1. Row 2, 0 or 1 is 1, 1 or 1 is 1, 0 or 0 is 0. So the bottom row is 1, 1, 0. Collect them. The join has rows 1, 1, 1 and 1, 1, 0. Watch where the only 0 sits, exactly where both inputs were 0, or tends to fill a matrix with 1s. Now the meet on the same two matrices. It uses and on each matching pair. Row 1, 1 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0, so the top row is all zeros. Row 2, 0 and 1 is 0, 1 and 1 is 1, 0 and 0 is 0, so the bottom row is 0, 1, 0. Collect them. The meet is all zeros except a single one in the middle of the bottom row. Compare the two answers, or filled the matrix with 1s, and nearly emptied it. That makes sense. Only one position had a 1 in both matrices, so only that position survives the meet. Now the Boolean product. Written A with a circled dot B, the sizes must match the way they do for ordinary matrix multiplication. A is M by K, and B is K by N. The inner sizes must agree, and the answer is M by N. To get the entry in row I, column J, we walk across row I of it and down column J of B we pair them up. A sub I1 with B sub 1J, a sub I2 with B sub 2J, and so on. For each pair we take the meet, the and. Then we join all those results together with or. So it is exactly like normal matrix multiplication, but n takes the place of times, and or takes the place of plus. In the example, A is 3 by 2 and B is 2 by 3, so their Boolean product will be 3 by 3. Now the solution, one entry at a time. Row 1 of A is 1, 0. We pair it with each column of B in turn. Inside each pair we take the meet, the and. Then we join the results with or. Entry C1, 1. Column 1 of B is 1, 0. So we form 1 and 1 joined with 0 and 0. 1 and 1 is 1. 0 and 0 is 0. 1 or 0 is 1. So C1, 1 is 1. Entry C1, 2. Column 2 of B is 1, 1. We form 1 and 1 joined with 0 and 1. 1 and 1 is 1. 0 and 1 is 0. 1 or 0 is 1. So C1, 2 is 1. Entry C1, 3. Column 3 of B is 0, 1. We form 1 and 0 joined with 0 and 1. Both pieces are 0 and 0 or 0 is 0. So C1, 3 is 0. The first row of the answer is 1, 1, 0. Now row 2 of A, which is 0, 1. Entry C2, 1. Column 1 of B is 1, 0. We form 0 and 1, joined with 1 and 0. Both pieces are 0 and 0 or 0 is 0. So C2, 1 is 0. Entry C2, 2. Column 2 of B is 1, 1. 0 and 1 is 0. 1 and 1 is 1. 0 or 1 is 1. So C2, 2 is 1. Entry C2, 3. Column 3 of B is 0, 1. 0 and 0 is 0. 1 and 1 is 1. 0 or 1 is 1. So C2, 3 is 1. The second row of the answer is 0, 1, 1. Now row 3 of A, look at it. It is 1, 0, exactly the same as row 1. Same row, same columns, same answer. So row 3 of the product repeats row 1. The Boolean product has rows 1, 1, 0, 0, 1, 1, and 1, 1, 0. Now Boolean powers. Let it be a square 0, 1 matrix, square so that we can multiply it by itself. Let R be a positive integer. The RTH Boolean power of A, written with the superscript R in square brackets, means the Boolean product of R copies of A, all combined with the circle dot operation. For the special case where R is 0, we define the 0th Boolean power to be the identity matrix, the one with ones on the diagonal and zeros elsewhere. One more thing. This definition makes sense because the Boolean product is associative. That means it does not matter how we group the factors. The answer is always the same. Finally, a full example. We are given a 3 by 3, 0, 1 matrix A, and we must find every Boolean power of it. Watch the square brackets in the superscript. They mark the Boolean power, the one built from and or. This is not the ordinary matrix power we defined earlier, and the two really do differ here. The method is simple. Each power is the previous power. Circle dot A so we build them in order and watch for the moment when nothing changes anymore. First, the second Boolean power. That is a circle dot A working the 9 entries the way we did before. It comes out as rows 1, 1, 0. 0, 0, 1, and 1, 0, 1. Next, the third power. That is the second power, circle dot A. It comes out as rows 1, 0, 1, 1, 1, 0, and 1, 1, 1. Watch the bottom row. It is filled up with ones. Keep going with the same method. The fourth power is the third power, circle dot A. It comes out as rows 1, 1, 1. 1, 0, 1, and 1, 1, 1. Only a single 0 is left. The fifth power is the fourth power, circle dot A. Now every entry is 1. Now the key observation, and it needs care. Take the all ones matrix and step once more. Every entry of the answer is the join of one whole column of A. Look at it itself. Column 1 is 0, 1, 1. Column 2 is 0, 0, 1. Column 3 is 1, 0, 0. Each column holds at least 1, 1. So each join is 1 and the answer is all ones again. The same argument applies at every later step, so the matrix is stuck at all ones. The nth Boolean power equals the fifth power, the all ones matrix, for every n that is 5 or larger. The powers stop growing.